The next one is going to be on functional groups. Okay, so basically organic compounds are grouped into families based upon common structural features. And what we call a functional group is a collection of atoms within a molecule that have a characteristic chemical behavior. So if you know the functional groups, you can predict their chemistry. So ketones will behave in a certain fashion when they are reacted with reducing agents like sodium borohydride. Hydroxyl groups will have a specific chemical behavior when they are, say, in the presence of sodium hydride or something like this. So you can basically predict their chemistry if you can recognize the functional group. And then what we're going to see is that certain functional groups are quite similar to other functional groups. And this type of the chemistry can be, it won't be necessarily identical, but it will be close. So the functional groups are, in a way, the alphabet of organic chemistry. It's just it's one of the pure memorization things that we need to do, because it's all about names. So the most basic functional group, and the one which is common in all of our compounds, are what we would call alkanes. And so an alkane is basically just carbons and hydrogens, all with single bonds. We use alkanes basically in gasoline for driving around in our cars. So they are certainly combustible, but with the exception of some radical chemistry, they tend to be unreactive. And so carbon hydrogens, carbon-carbon single bonds, are going to make up the backbone of most of the molecules that we look at. So this is the one functional group where it's basically, you can find an alkane portion of it in almost every molecule. So we almost don't count it. When I say, okay, what functional groups are present? We usually don't name alkanes because they're in everything, or pretty close to everything. Once you, where's my little, there we go. Just trying to get my laser up. Okay, once you add a double bond to your carbons, we call these alkenes. And so there's a pi bond between two of the carbons. And so pi bonds are certainly more reactive than sigma bonds. And so the chemistry of alkenes can be markedly different than the chemistry of alkanes. When you add another pi bond between the same two carbons, we call these alkynes. And so these are triple bonds. And alkynes, the chemistry of an alkyne is quite similar to an alkene. In certain reactions, this can react a little bit more because there's another pi bond to react. But we'll do a section in Organic 1 where we did a whole bunch of reactions with this. And then when we stepped over to the triple bonds, they are very similar. So these are the functional groups which just involve carbons and hydrogens. So no heteroatoms at all. So alkanes, alkenes, alkynes. Then when we move into the heteroatoms, probably the most common one will be oxygen. And so an alcohol is when you've got an OH group attached to a carbon. And these are all with sigma bonds, so single bonds. So there's a generic name for just a OH group, that's a hydroxyl. But the hydroxyl fragment is found in a number of different functional groups. So it's found in an alcohol when there's a carbon here. So alcohols contain a hydroxyl group. Some other functional groups contain a hydroxyl group as well. So carbon, oxygen, hydrogen is an alcohol. Its cousin, carbon, oxygen, carbon, is called an ether. So oxygen is bonded to 2 carbon atoms with sigma bonds, whereas here it was just 1 carbon and 1 hydrogen, both with sigma bonds. So alcohols, like the physical property of an alcohol is different than that of an ether because of this OH bond. And when we talk about intermolecular forces, we can hydrogen bond with this hydroxyl group, whereas in ether, there's no hydrogen here to hydrogen bond with. So ethers tend to be more volatile than alcohols. Ethers are relatively unreactive. So in organic, we see that these are often used as solvents too. So carbon, oxygen, carbon is an ether. Carbon, oxygen, hydrogen is an alcohol. Now, when you've got carbon, which has got a single bond, a sigma bond and a pi bond, so a double bond to an OH, this is generically called the carbonyl. And there are numerous functional groups that have the carbonyl. So if the carbonyl, so the carbon-oxygen double bond, is flanked by a carbon and a carbon, we call this a ketone. If we replace one of the carbons with a hydrogen, this is called an aldehyde. So you probably have heard the term ketone or aldehyde before, and this is basically what they look like. So a carbonyl flanked with hydrogen and carbon, or a carbonyl flanked with carbon and carbon. So the chemistry of ketones and aldehydes are very similar. Aldehydes tend to be slightly more reactive because this hydrogen is very, very small, and so it's easy for other molecules to attack this. Typical reaction. Now, if you've got a carbonyl that has got a carbon on one side, but on the other side it's flanked by a hydroxyl group, we call these carboxylic acids. Acetic acid would be the most common. And yeah, acetic acid, like so vinegar, that would be the most common or basic carboxylic acid. And in the name, it basically says that this compound is an acid. So this proton here is the acidic proton, which gets donated in the presence of a base. Esters are a derivative of a carboxylic acid, except for we're replacing the hydrogen with the carbon. So carbonyl flanked by carbon, and on the other side, oxygen and carbon. So if you go back to your alcohols, alcohol and ether, it's basically the same thing here. Like we're replacing hydrogen with carbon to give us an ether. In the case of an ester, you start with your carboxylic acid and you make it ester. The only difference is, of course, that there's a carbonyl in between there. So carbonyl, replace this OH or this H with the carbon, you got an ester. Esters smell wonderful. Most nail polish remover has got a combination of ketones and esters in it. A lot of perfumes are esters. They've got wonderful fruity smells. They are awesome. They smell good. And then there's some other really interesting functional groups with the carbonyl as well. So the next one is if we replace the oxygen with a nitrogen. And of course, nitrogen can be bonded to 3 different things. So I put hydrogen or carbons here. This is what we call an amide. And this is super important in biochem. Amide linkages make up like all of our like amino acids, peptides, all these types of things are made by amides. And if you go to America, they pronounce it amides. It's funny, there was a talk where this fella from America was giving a talk and he was talking about these amides and I was like, what? And I was thinking to myself, did I miss something when I was younger? Anyway, it's an amide. So the amides can be classified further to primary, secondary, or tertiary, depending upon if we've got carbons here. So if it's just 2 hydrogens, we would call this a primary. If there's a carbon and a hydrogen, we'd call it secondary. We'll get to that a bit later on. It's not important for what. The important part is that carbonyl with carbon on one side and nitrogen on the other is an amide. If you've got a halogen here, these would be called acid halides. So if it was a chlorine, it would be called an acid chloride. If this was a bromine, it would be called an acid bromide. And the last important one, I guess, is when you've got a carbonyl, oxygen, carbonyl, and then there's still carbons on either end. These are anhydrides. Acid halides and anhydrides are basically synthetic compounds. They're really reactive, so they don't survive in nature particularly long. There is the odd biochemical process which might involve an anhydride, but by and large, they react quite quickly in the presence of water and that type of thing. So that's the carbonyls. We would have heard the term amines in Gen Chem. And so this is nitrogen, which is bonded to carbons. And so carbon, nitrogen, and then hydrogen or carbon, doesn't matter. These would be amines. And so if we've got 3 carbons, that would be a tertiary amine. If it's got 2 carbons and a hydrogen, that would be a secondary amine. And if it had 2 hydrogens and 1 carbon, it would be a primary amine. But these compounds are basic. So I think that's what we would have. So NH3 ammonia in Gen Chem would be the most basic amine, I guess. So let's see, carbon, sulfur, hydrogen. These are thiols. And this is the equivalent, if we remember, sulfur is right below oxygen on the periodic table. So this is basically the sulfur equivalent of an alcohol. So thiols is the most generic name of this. There's a couple others that are used that you can find in textbooks, mercaptans and stuff like this, but really it's just a thiol. That's the easiest one. Skunks produce some of this. Thiols tend to smell awful, and thiol ethers. So carbon, sulfur, carbon. So this is the sulfur equivalent of an ether. So thiol ethers are sulfides. These stink to high heaven as well. It's strange. There's the odd one which smells really good, but the rest of them are just awful, awful smelling things. So, all right. And then sulfur can be oxidized, so it can form double bonds with oxygen. And so there's a series of functional groups that are important, that are, like you would think that this looks like, if we replace this with a carbon, this would be like a ketone, right? So a sulfoxide is basically the sulfur equivalent of a ketone. The only difference is that sulfur can have an expanded octet, so it's got these lone pairs here. and then we've got sulfone. So this is the one which is based off of the ketone. So sulfone, where it's full, the sulfur is fully oxidized. So there's 2 double bonds to oxygen. So this always reminded me of sulfone, sulfoxide, when there's just 1. And then what we're going to do, like we did with the carbonyls, is we're going to replace this carbon with an OH, or we're going to replace this with a halogen, or we're going to replace this with a nitrogen, and we're going to get the other functional groups, the last ones. So when we replace sulfur with an OH, sulfonic acid, so it's the base of the sulfone, and you just convert it to an acid. So carboxylic acid, sulfonic acid. So it's similar to the carboxylic acids. O carbon, so this is like the ester, sulfonate. If you do nomenclature of organic compounds, the 8 part is what you would call an ester. So if you're ever looking at a bottle and the ingredients and it's got an 8 on it, that means that compound's an ester. So they just put the sulfone part at the start, so sulfonate. Sulfonic acids are really powerful organic acids. Sulfonates they're used for a number of different things. Often these are designer compounds that have been created for a specific task. In organic chemistry, one of these tasks is the sulfonate can become a really good leaving group. So it's used in that chemistry to make this carbon here electrophilic. We'll get to that for all of you who haven't gotten there yet. Sulfonamide is the equivalent of an amide. This is the functional group that I like the most. It is similar to, of course, the amide. And so these are often used in medicinal chemistry for a whole bunch of reasons. They're they were used at the very start of medicinal chemistry because they possess a whole series of antiviral, antibacterial properties. So they're used an awful lot in medicinal chemistry. So it's a really interesting functional group to use. And then sulfonyl chlorides, this is a completely synthetic sort of compound where you were replacing we've got a halogen here. And in fact, sulfonyl bromides and stuff are quite reactive. So this is the one which you can find commercially, but it isn't necessarily, it's not a natural compound, it's a synthetic compound. So those are the, no, there's 2 more. Good. These are all of the ones which are based upon basically the sulfone structure here. So sulfonic acids, sulfonates, sulfonamides, sulfonyl chlorides. Sulfoxides, there's one very famous sulfoxide that's used as a solvent. These can be really, really good solvents for organic compounds because they're very polar, but they are organic. So they're capable of dissolving organic compounds plus inorganic compounds. So sulfoxides are really, really good organic solvents. All right, so the last 2 are aromatic rings. So a 6-membered ring that has got double bonds. So these are basically, we would say that this is an aromatic compound. So it's slightly different than an alkene because of the fact that the double bond is in a ring system. So that is important. Alkyl halides, amine carbon bonded to a halogen. Alkyl chloride, alkyl bromide, alkyl iodide. Oh, and when you've got an aromatic ring and it's got a hydroxyl group on it, that's a special type of alcohol, which is called a phenol. So let me see if I can draw something. So this little fragment, so it's an aromatic. If this fragment is bonded to something, we call, it's been given a name like a phenyl group. So if it's bonded to an OH, they use a prefix for the phenyl, and then the prefix for the alcohol, which would be phenol. And so there are certain functional groups that when you combine the two of them, like an aromatic ring and an alcohol, there's a special name for it. So phenol is one of those names. Well, we'll get the hang of that a bit later on. All right. So those are the basic, stop that. Those are the basic functional groups that we're going to see throughout the course. Now, one of the things that would always be useful is to go through and draw some generic sort of molecule with, say, a double bond in it. Like this doesn't necessarily need to be a hydrogen here, but do them, like, say, add a whole bunch of carbons to this and determine what the molecular formula is and calculate out what the double bond equivalents are. And similarly with an alkyne, just maybe replace a hydrogen, put some carbons here, and make sure it's got the correct valency for hydrogens and stuff, and calculate out the double bond equivalents for each and every functional group. Because what that's going to show is that it's going to give you a hint as to, like, I can see here that there's a double bond here, so this should have a double bond equivalency of 1. But with some of the other one, like, it's just a good practice to get the hang of it. That's why I always suggest people do. Draw some molecules which have, like, perhaps 1 functional group or maybe 2, and just get some practice calculating out the double bond equivalents. And so what we're going to see in the infrared section, so when we start infrared on Thursday in the morning, what we'll do is just how the machine works and what it's looking at. And then, because we'll divide the class sort of into 2 halves because it's a 2-hour course. And then in the second half, what we'll do is we'll look at some spectra about some different functional groups and what they look like. So what we're going to see is that a OH functional group, a hydroxyl group, behaves quite differently than a carbonyl. And a carbonyl is going to behave differently than, say, an alkene, because an alkene is a carbon double bonded to a carbon, whereas a carbonyl is a carbon double bonded to an oxygen. So the infrared spectroscopy, that's telling you what functional groups are present. And then we're going to use other evidence to actually put them all together to make the molecule which we're looking at. So that's basically how it's going to work. It's a little preview for next week. And it looks like I ran over time. 12:30. Sorry about that.